Okay, so we've kind of called it quits with shock waves, right? So let us sort of begin with expansion waves, right? Let's see what that means, and so let's. It's usually called Prandtl-Meyer expansion waves. So let's begin. Now, what we've done so far is that you have a so if you have, say, a supersonic flow, say if you have, say, a supersonic flow, right, and then you have an obstacle like that, so you have a compression corner like that, there is shock waves, right, shock wave like that, it turns the flow, etc. Okay, or if you have an incident flow like that, you have a normal shock, right? So this is supersonic, and then this here becomes subsonic, and this here for a for say an blunt body could be a combination of subsonic and supersonic, and depending on this Mach number m2, depending on whether this is an oblique shock, is a strong shock or a weak shock, based on that this can be supersonic or subsonic. Okay, so basically what we've done here is that we have a flow which comes here and we kind of block it, right? We block it, and hence we are changing its properties here. Now let's try to do exactly opposite to blocking it. Okay, instead of blocking it this way, why don't we try this? Okay, instead of blocking it, right? So let's try this. Let's expand it, right? Instead of blocking it this way, let's expand it, right? So we were, say, blocking it by a theta like this. Instead, let us allow it the corner to expand it, and let's see what that means. So basically, say if I have a flow like that, right? If I have, say, a flow like that, and say it encounters a corner like this, okay, a corner like this, right? So what we have seen so far, is this. Right? We have seen this, so that there is a shock wave which comes. Instead, now we are saying, instead of blocking the flow like that, let us expand it. So we have something like this. Okay. So in this case, what will happen is that the flow will actually expand over this here, and then continue to flow past it. Okay. So hence the name, basically, expansion fan. So let us sort of draw it in let us begin. So let us say, right, and say you have this. Okay, so this is the region on which it sort of expands. Okay, this is the region in which it will expand. So what happens is that this comes like that, it moves like this, and then it moves past it. So then this is my M2. So similarly, we can have other streamlines which comes like that and moves past it, and it expands over this region and moves past it. Okay. So what we are interested now is in this region. So we will talk about this, we'll detail this a little more. So usually this is the kind of diagrams that you will see in general books, etc. So this region is essentially the shock wave, sorry, the expansion wave, right. So, this is actually called the Prandtl-Meyer Prandtl-Meyer expansion, Prandtl-Meyer expansion wave. Okay. So, now essentially as we talked about in the last lecture, that these are a collection of Mach waves. Okay. So, essentially the Mach wave is a very weak, or the limiting condition of an oblique shock, right. So, therefore, if you increase the deflection angle a little bit, so then you will start getting a shock, and you get this shock becomes stronger. So, the weakest shock, or the limiting condition of a shock, is the Mach wave. So, these are fine disturbances, right. So, if you have a supersonic flow like that, and which you are making it pass through a corner like this, you are making it expand through a corner like this. So, it will do so over a region of disturbances which will look like this. So, like we showed, like we discussed yesterday, right. So, these are lines which are basically for different Mach waves. Okay. So, in this case, so therefore, if I were to, let me sort of define this. So, so say these are the two, the first and the last Mach numbers. So, therefore, this this angle, right, this angle, the angle of the first one is, let us call, say this is the Mach wave angle, this is mu1, okay, and the angle that this is making is mu2. So, basically what we are saying is that this, right. So, what basically is that, okay, so let us say this is the, this is say 1 and 2, right. So, the starting, so starting Mach wave is making this angle with this surface, right, and the end Mach wave is making mu2 with this particular surface, because what you see here is that this Mach wave is therefore here, in the surface, and then it expands, the surface has actually changed, which is this. So, therefore, we take the angle with this surface here. Okay. So, this is essentially my Mach wave. Now, so what exactly is the, so if I consider this as the first region and the second region over here, okay. So, what we will see is that what we will see over here is that, okay. So, okay. So, then, okay. Okay. Now, if this is the case, the continuity equation still holds, right. So, we have the continuity equation, right, which is so rho 1 u1 is equal to rho 2 u2, right. But what happens here is that rho 2 is less than rho 1. What this implies, okay, what this implies is that u2 is greater than u1. Okay. So, what this is meaning is that the flow, what is coming here, actually starts moving faster beyond faster due to the expansion fan. Okay. So, this is what we get from here. So, the upstream side here, okay. So, this is say M1, okay. So, this is M1 and here it is M2. So, let us call this is basically M1 and this is M2, right. So, just to get all the parameters in place. So new one, right? Okay. So new one is equal to sine inverse 1 by m1, right? Okay. And new 2, right? Essentially these are Mach waves. So the Mach wave angles are given by this. This we discussed in the last lecture. Okay. So this is what we, so this is how the structure looks like. Okay. So now therefore what we are seeing is that due to this turning angle, so let's call this as say theta. Okay, let's call this as theta. So what we are seeing is that again, if we turn this flow, right, turn this flow by an angle theta, there is again a change in property. The change in properties in this particular case is due to this expansion fan. So clearly what we need to do now is find out the relationship between the change in properties and this theta, right. So by how much if we change for say an infinitesimal change in theta, what is the corresponding change in the properties, right. That is what we have been doing so far. So we will do it for this case as well. Okay. So now so let's say now let us look at just say one Mach wave and understand a few things here. So say this is a Mach wave, right. So we have, this is a Mach wave. Okay, let's just draw that here. Right, this is a Mach wave and this is an say this is your this is just for a general Mach wave, right. So then this is the Mach number and this is the incident velocity, okay, and it encounters the Mach wave and then it so therefore the velocity here increases, isn't it? What we showed here was that as the flow goes past a Mach wave, the velocity is increasing. It moves faster beyond a Mach wave. So if the velocity is the incoming velocity is v, so it encounters this Mach wave, it starts traveling faster, right? So it starts traveling faster. So let that be v plus an incremental change in the velocity, and this Mach wave is making. So let us look at these angles here. So say this angle is mu. Okay, this angle is mu. Now let us sort of complete this rectangle here. So let us look at this. Okay, so now if we are looking at this geometry over here, okay, so let us look at say. So if we look at this triangle over here, so this angle is 90 minus mu, isn't it? So this angle minus mu, okay, which makes this angle what? Okay. So if that is so, and let's say that this angle, so let's say that this has been turned by say d theta. Okay. So this Mach wave is able to turn the flow by an angle, an incremental angle d theta, right. Then what does it make? What is this? So now if this is it, so let us consider this point as C. So sorry, let's consider that as D. So if we consider the triangle ABD, then this angle turns out to be pi by 2 minus nu pi by 2 minus nu minus d theta, right. This is just simple from this geometry. Okay. Now, if I do that, okay, if I do that, so this is basically, so this was the velocity, right, this was the incoming velocity. So, now this is the, say, the incoming velocity v. Now, let us consider the triangle ACD. Look at the triangle ACD. Okay. If I do that and using the law of sines, this is from basically the math, right. So, if I use the law of sines, what we get is that v by pi by 2 minus nu minus d theta, okay, is equal to v plus dv by sine pi by 2 plus mu, right. This is what we get. So, therefore, we can write that v plus dv okay, by v, say, okay, v plus dv by v is sine pi by 2 plus mu by sine pi by 2 minus mu minus d theta. Okay. So, basically this is what we get, and if I do this. Okay. So, here now if I write this out, okay, so if I am going to use this, now we also know that v is equal to, okay, so now this we also know this, right, velocity is Mach number into speed of sound. Now, from the, so if I differentiate this, so what I guess is sorry. So, if I take log here and then if I differentiate, right. So, what I get is dv by v is dm by m plus by A, right. Then for a calorically perfect gas and for adiabatic energy equation, what we get, okay, so what we get is this. These are relations which we've sort of been doing so far. So, hopefully you can recall. So, gamma minus 1 by 2 m square. Okay. So, essentially what I am saying is that so we get this relationship. Now, when we have this here, right. So, what we will basically do is write, if I were to expand this etc., this equation, then I will be able to write it like so. So, let us erase this now. Okay. So, we have these two relationships, we have this and this out here. Now, this relationship I can write it in this form. So, d theta is equal to m square minus 1 dv by b. Okay. So, this relationship, if I expand etc., so I can write it in this form. But again, if I were to write this over here, right. Okay. Now, dv by v, right. Okay. So, therefore, this is a relationship. Now, we just saw actually that v is equal to m a. Okay. So, we said ln v is equal to ln m plus ln a. So, therefore, if I differentiate, I get dv by v, which is equal to dm by m plus dA by A. Okay. Now using, so therefore dV by V is equal to this relationship. Now then in this I am going to use this relationship over here. With the combination of this and this, I can write dV by V, okay, dV by V in terms of the Mach number, and I can write that as okay. Okay. So, basically using this, so these relationships, then I am going to change. Okay. So, the velocity terms in terms of the Mach number. Okay. So, this is what we get. So, therefore, okay, so what we can write is that d theta is equal to, what we get here is that d theta is equal to under root m square minus 1 by 1 plus gamma minus 1 m square Okay. So, what we are seeing over here is that for a given Mach number, right, for a given Mach number, if you turn the if you or for example, if you turn the flow for an infinitesimal change in the turning angle d theta, this is the relationship between the change in the Mach number and the change in the deflection angle, right. So, this is basically the differential equation which governs the Prandtl-Meyer expansion fan, right, and this is the Prandtl-Meyer relationship, okay, Prandtl-Meyer equation. Now, we are going to work a little bit along with this. Okay. So, therefore, what we see over here, essentially if we come back to this diagram here, okay. So, so therefore, say this one, let us just say that this is say theta 1 and this is theta 2. Of course, theta 1 is 0, okay, and theta 2 is theta. Okay. So, what is happening is that we have a Mach number, we have an incident Mach number of m1, it encounters this expansion corner and it goes from theta 1 to theta 2. And what we have found out is that for if I have this incident wave and I right. So, I have an incident wave and I deflected by or I expanded by an infinitesimal angle d theta, right. If I do that, then the relationship of this change in the deflection angle with the Mach number on the Mach number beyond the expansion wave, right. So, therefore, what we can say here is that, okay, so let us sort of write that again. Okay. So, having done this, this is like basically for a single right. So, what we have is that we have this Mach number, right, we have this Mach number, right, and we have this sort of an expansion fan. So, it goes through that and okay. So, this one is theta 1, this one is theta 2. So, this is equal to 0, this is equal to theta, that is this angle is equal to theta, right. So, therefore, the relationship that I have is that d theta is equal to under root m square minus 1 by 1 plus gamma minus 1 by 2 m square dm by m. Okay. So, this is the relationship. So, therefore, for an incremental, deflection, the corresponding change in the Mach number. Okay. So, in this case what we will do is, I think, for a total change in angle from theta 1 to theta 2, all we will do is integrate this. Okay. So, if I integrate this between theta 1 to theta 2, right. So, if I integrate from theta 1 to theta 2, it basically goes from m 1 to m 2. Okay. Now, this integral, this integral is called as the Prandtl-Meyer function. So, this integral right. So, this integral, so which is a function of the Mach number, isn't it? So, this integral is called the Prandtl-Meyer function. Okay. And if we do this integration, what we get is this. Okay. Let us write this out. Okay. So, basically this is the integral right. This is the integral, and if I do this, okay. So, I am not sort of doing the steps or whatever, you can try it on if so you please. So, okay. So, this is tan inverse, which is gamma minus 1 gamma plus 1 m square minus 1 minus tan inverse m square minus 1, right. So, therefore, this is the Prandtl-Meyer function. So, Prandtl-Meyer function. Okay. So, as you can see that if for a given Mach number you have a different Prandtl-Meyer function. So, Prandtl-Meyer function, and there is, so this basically what we are talking about here is that this is the expansion fan. So, expansion fan basically consists of several Mach waves, right, and the limiting Mach numbers are m1 and m2. So, all these have different Mach numbers, right. So, these will basically go through a series of, these will suffer a deflection, this will will suffer or will expand through this fan. So, step by step when it encounters each and every Mach wave, right. And this Prandtl-Meyer function is basically defined for every small incremental change in the theta and the Mach number. Okay. So, therefore, if I write this integral as in this form, which is the Prandtl-Meyer function. So, then coming back here, so my total change in theta, that is in this case theta goes from theta 1 to theta 2, which is 0 to theta, right. So, which becomes theta. Okay. So, then that I can write as Prandtl-Meyer function m2 minus m1. Okay. So, m2 minus m1. Okay. So, this is essentially the relationship. Okay. Now, in here if I had to just sort of okay, yeah. So, now what we will do is, let us sort of do a problem and see that how we are going to use, or what are in the tables and so on and so forth. Now, what you will see in the tables again, now when you see this Prandtl-Meyer function, so basically what you see is, if a Mach number is given, then this can be plotted, I mean you can immediately calculate this for any given Mach number. You can calculate this for say gamma is equal to 1.4. So, and also Mach wave angle is sine inverse 1 by m. So, the Mach wave angle also can be calculated. So, therefore, what you have in the standard charts is this. What you will have in the standard charts is basically a listing of the Mach number, the Mach wave angle and the Prandtl-Meyer function, right. So, this is what you will have for the Prandtl-Meyer expansion waves. The standard chart will have the Mach number, corresponding Mach wave angle and the Prandtl-Meyer angle. Okay. So, let us therefore look at a problem. Okay. So, let us look at a problem and see how we can use this chart or what else you can use. Okay. Okay, so what is given? What is given is that this M1 here, okay, what is given is M1, right, M1 is 1.5, P1 is, okay, so you can convert this to SI units. I usually do that, didn't get a chance to do this today. So, you can just do that, and T1, this is given in Rankine, so you can convert that, just Google it, and you know, you should be able to convert these to SI units to Kelvin and say Newton per meter square. So, okay, so M1 is this P1 and T1, and theta is equal to 20 degrees. Okay. So, essentially what we have is that we have this flow which comes in with Mach number this, pressure and temperature, and it goes through an expansion corner, the angle of which is 20 degrees. So, this is 20 degrees. What we are asked to do is to find out, basically this is the region 2. So, what we need to find out is P2, T2, M2, stagnation conditions, and also Mach wave angles mu1 and mu2, because clearly you need to find out what is the angle, here, okay, mu1 and mu2. So, these are things that we need to find out. So, this is basically the problem. So, how do we go about this? Okay. So, what do we do and how do we go about this? So, what you can straight away see is that for the Mach number 1.5, so go to your charts, for Mach number 1.5 you can get nu1 and gamma m1. Okay. So, you can get this from the charts right away, just look for 1.5 Mach number, and so let us go step by step here, right. So, let me write this. So, first step is that Prandtl-Meyer, so go to the tables, okay, for M1 is 1.5, you get the corresponding Prandtl-Meyer function to be equal to 11.91 degrees, which is around 12 degrees. Okay. So, this is what you get. Then yes, and we get also the, so this is nu1 actually, which we get that as 41.81 degrees, which is around 42 degrees. Okay. So, therefore, now what do we do now? So, that is all the information we will get. Okay. That is all we will get at this point of time using Prandtl-Meyer tables. I can only find out the Prandtl-Meyer function and the Mach wave angle. Okay. What do we do now? Well, we had a relationship which we said, so theta is equal to m2 minus m1, right. So, this is what we had derived for our expansion fan. So, we said if it goes through an angle which is deflection angle of theta, then that is equal to gamma m2. So, Prandtl-Meyer function for this minus Prandtl-Meyer function for this. So, this angle is known to us, theta, which is 20 degrees, right. This is something that we do not know. This is something that we found out, which is right. So, therefore, what we can do now is find out this, which is equal to, right. This is what we get. So, once we get this, so now what we do is we just go back to the tables again. We go back to this table here. Now, instead of the Mach number or mu2, what we have is this. This is available to us, isn't it? In the first case, this was available to us, so we found out these. In this case, now this is available to us. Okay? So, this is something that we were able to find out. So, here corresponding to the Prandtl-Meyer function, we'll go the reverse way and find m2 and mu. So, what we had here, this one was m1. So, we were able to find nu1 and m1. Now, this is nu, well, we can say this is nu2, right. This is what we know. So, correspondingly, we will find out nu2 and m2, right. So, we do that. So, what we find is that the corresponding Mach number is 2.207, around basically 2.21. Okay. So, that and the corresponding nu2 is 26.95. So, the Mach wave angle. So, what we get here is that the incident, this mu is 11.91, right, or no, 41.81. So, this was around say 42 degrees, okay, and this nu2 is, so this angle is around 27 degrees, around 27 degrees. This is what we get. Okay. Now, once we have done this, okay, now, so we are done with the more or less the definition of the geometry, etc. Now, we need to find out the properties. So, P2, T2 and the stagnation conditions. Okay. How do we go about doing that? Now, as I said in the outset that all of this is isentropic relationship. So, the flow across this, the expansion across this fan is isentropic. Okay. So, it is isentropic, and which means that the entropy change is 0. Okay. If that happens, then what do we do in this case? What do we know immediately? Right, because of the isentropic condition, this is what we get right away. Now, so because it is isentropic, we will go back to the isentropic tables. Okay. So, we go back say to the isentropic tables, right. We go back to the isentropic tables, and so for the first case now, right, m1 is 1.5. So, for this here, so we go from m1 equal to 1.5 to m2 here, right. So, this goes like that. So, this here, this is m2 is so around 2.2. So, basically, so the Mach number has increased, right. So, let us go at m1. Okay. So, for m1 equal to 1.5, right, m1 equal to 1.5, what we get is so around 3.7 and T naught 1 by T 1 is 1.45, right, and for M2 equal to 2.207, right, what we get is P naught 2 by P 2, right, which is 10.81, and T naught 2 by T 1 T 2 is around 2. Okay, so how do we go about? So basically we need to find out P naught 2 and T naught 2 and P 2 and T 2. So how do we go about doing that? Okay, so what we see over here is that P 1 and T 1 is given, right? P 1 and T 1 is given over here, but how do we incorporate that? Now, what you see here is that from these two relationships, right, P 1 and T 1 is given, so these two can be calculated. So, this 2 you can calculate because these are given, is not it? This and this is given, right. So, you can calculate this P naught 1 and P naught 2. Main aim is we have to find out P 2 and T 2. What do we do? Well, because it is isentropic, so P naught 2 is equal to P naught 1. So, the value that you calculate here you put in here. Okay. Then T naught 2 is equal to T naught 1, again because it is isentropic. So, again you use this value of T naught 1 which you calculate and put it here. Okay. So, once you do that, so using that what we will get is P 2 and T 2. Once you this, so this is basically it has calculated. So, this is available. Okay. It has been calculated. So, then you evaluate these two values. Okay. Then you evaluate P 2 and T 2. Okay. So, that pretty much gives us, so that is how we go about calculating the properties across an expansion shock. Okay. So, pretty much just use the Prandtl-Meyer tables and then go about calculating the property change. There is so mu 1. So, this is making mu 1 and this is mu 2, right. Now, let us just calculate the so M 1 essentially this before this the starting Mach wave, okay, that is the angle with the horizontal. What is the horizontal? The angle that this wave, the aft wave, that makes with the horizontal, which is just 27 minus 20, right, is not it? That is around 7 degrees. Okay. So, this angle that it makes here, you can calculate this. This is just for slightly, this is around 7 degrees. So, we have basically completely defined or the geometry as well as found out the properties across this expansion shock, expansion wave, sorry. Okay. So, so essentially, so this is about, this is one class that we will do on expansion fans. What we will move on to now is some unsteady motion, right, the shock tube, okay, which is I think very interesting. So, this is that, and I think we will stop here today. Okay. Thank you.